Good day to you all. Shall we pray? Oh Lord, thank you this day. We exalt your name above all things. We say as we start this class, ENG 202, cantilever, and some other topics, that grant us the revelation, knowledge, and understanding. So that we may understand how we've learned and how we're going to learn. To then pray that we might be more expound and understand more. So your name be highly exalted. For this name we pray. Amen. So this cantilever, continuation of the last topic, that is shear force and bending moment. You've talked about point load of a diagram like this. You talk about UDL of a diagram like this that have different distributed load around it. You've talked about UDL, something like this, and we've talked about running combined load. We're talking about cantilever. Cantilever, like it is hinge to the wall, or is hinge, something like this. So we are considering something like this, and we are also considering combined load. Combined load can be in form of, it has cantilever, when you have cantilever on top, when you have something like this, when you have UDL on top, you have different kind of load acting. You now consider everything like that. So we're considering cantilever. Now cantilever diagram is like this. Say for example you have this thing into the wall, this beam into the wall, and it is somehow of this length, and you have a weight acting on it at the edge. Let's say this is W. So this is the length. The length given is, let's say, X. Okay, the length given is X. Or let's say L. Okay, let's say L. The length given is L. So therefore, you can simply write this out. This is loaded cantilever. We have the shear force diagram, we have the bending moment diagram for every of it. We're gonna be considering that as well. So the point load we have here is equals to your weight and is measured in kilonewton. We have the length, that is the total length, as L in a meter. So next thing I'm gonna do here is I'm gonna take my as you should, you're gonna take your, just take your check on diagram. So here you don't need to, your reaction, this is, let's say this point A and this is point B, or either way you want. So let's say this point A and let's say this point B. Either way you want, you're gonna pick a point. But if you're given the specified thing, you don't need to. So this point here, you don't have your RA equals to RB. You don't have RA plus RB here because there's no force acting. This is inch already. So in this case here, next thing you do is you find the shear force. So the shear force here is just simply W times the length, right? So but here shear force talking about the weight alone. So at point A, the shear force at this point A is TA. So shear force at A, when X equals to B rather, is still the plus, is still a plus weight. Shear force, it distributes like continuously like that. And imagine there's another weight here. Okay, let's continue this first. At this, you see also your the shear force there. You see also at X equals to A, it is maximum at S equals to, but other than there is no weight acting on this. Okay, assuming there's no shear force acting on this, it will be 0. Okay, so what the shear force acting on it, that is what is still your W, and what till it got here is still the same thing, and at X equals to, you see your what, W there. Okay, so now bending moment, when that is when X equals to, when X equals to B, it's 0, because why is because this point there's no particular thing acting on it. It's still zero, don't forget, like previous said. So that is 0 kilonewton meter. This is just kilonewton. So now bending moment when x equals to a is same thing as you saying that is negative, because it's acting at a. It is maximum at a. Why is because that'll be your load multiplied by the total distance. That'll be minus wl. You know, it's acting down. That is negative. It's actually negative to this guy because that is fixed, so it is always negative. Okay, it's always negative. And now you want to do your shear force diagram. You're gonna have something like this. You have something like this, and once I have something like that, I gotta put my shear force diagram here. I gotta put my bend diagram here. So having got this as well, I just want to draw. So at this point here, my shear force diagram is very fixed. So at x equals to is still what w, right? So I get to measure my length w, and you see w length. So it's just straight because it's still the same thing throughout. So I get to b till I get to a, and in this case I can have it as, you see this point here. So you can sometimes you can say it's negative, like negative. And don't forget, rather you can draw it down because it's acting downward. So you can draw like it's acting downward. That is negative. The negative, and that's shear force diagram. And your bending moment diagram, that is cantilever diagram. So that is the point diagram. So for bending moment, it will be like this because it is hinged at the wall. The load is fixed here. So what will happen is it will just somehow be something like this. It will distribute straight, so straight. That is cantilever, and that is negative. And you know when it's negative there, what do you have? It's for sagging. When you have a negative, that is what's organ. So this is organ here, organ here, organ, HOGGING. Okay, so that is that about that, and that is organ. So let's consider this example. So organ here, organ, HOGGING. Okay, so you can see it will just come down straight, and that is negative. Okay, so let's consider this example, this cantilever, and let's consider this example for cantilever. Okay, so here's a question. You see cantilever diagram. Yes, you have the cantilever here. You're not given any points for your direction, so you can just be given here as B and here as A. Sometimes you will not be given the points, you won't be given the span, you'll be given the span. The span means the 10 meter. You'll be given the points like A and B. So in this case here, you're given some certain parameters, so you gotta find your shear force and bending moment itself. So first thing you do here first is you add the span. That is the parameter out. That is for the beam, you have the span as, that is this length. The span means the length. So you can have the span, which is the length. The span here is what? 10 meter. So next thing you write is you find your point load. Okay. So what is your point load? Your point load, you should know that you given 5 kilonewton per meter. It signifies the point load. So the question is to draw shear force diagram and bending moment diagram. So the point load here was your WL, right? And that is your WL is what? 5 times 10. That'll be 5 times 10, that'll be 50, right? That is 5 kilonewton per meter times 10 meter, 50 kilonewton. And you know, for UDL, the question or the diagram, or for UDL, it will always come to the center. I've explained that in last class. So this is just the point load, believing or open or knowing it, we are at the center. And that is that. So next thing you find also is you find your, you also know you have your particular point load here as well, which is your UDL. So here my UDL, which is my W, is I gotta find my UDL, which is my W, is what, 5 kilonewton per. So these are the parameters we have on this question here. So next thing you write out to show shear force down that main diagram is for for any reaction here. Your shear force diagram or your shear force question or your shear force solution here is this. Let me draw it so we can draw a diagram here. So that will be my shear force at x equal to b at point B. First thing I find is that the shear force at that point is equivalent to the value of the force I have on that point. That is the shear force. So my shear force at that point X is equal to, at point B rather, is equal to what? 15 kilonewton. Now, and don't forget that is negative, it's acting downward, negative. Okay. So next thing also is that for the shear force at X, so now when I will section, for UDL, you must section it. This is a force acting on its own point load. Why this is UDL? Sometimes you might be very lucky to be given in when you are given like this, but not most times. Sometimes you can just be given the parameters. It's UDL. Okay. From the explanation, this is UDL. Now, it's very important you section your UDL. You section it since it's UDL. You distribute it. So we can decide to split this into, let's say, 2 meter. This is 2, 4, 6, 8, 10. But regardless that, it will distribute accordingly. So you should do not just waste time on that. So you can therefore split into 2, 4. Sometimes this is 10, you can just split into 5, 5, not to waste time. Okay, so like from that, you can do the next thing to do it to apply that. So at point when it is x equals to 5, because this is distributing at this edge, it gives us edge to solve this once ago. So at point x equal to 5 meter, this is when x equal to 0 meter. At 5 meter, what you do in x is that, if you remember, there's a force acting here which is 15, right? So at this point, which is 15 acting on this edge, the next thing you do is the shear force there is will now be the 15, but here you can find it as a positive, or so there will be 15. You can say minus 15 minus, okay, which is acting down, okay, clockwise equals to anti-clockwise. So minus 15 is acting downward. Minus 15 minus, that is for this 15. Minus 15 minus, if you cut this now, for the next one at point x equal to 5, that is, if you cut here, the force you'll be having will be left with what? This particular 15, and you'll be left with that other as well. So this is 15. If I convert this to my point load, I'm going to have this as what? 50. Right. So if I will convert this to my point load, I'm going to have this as what? 50. So that will be 5 times 10, 50. So that will be minus 15 minus 5 times 10. That will be, before I continue, so that means at this point, when x equals to 5, it is 50. I convert this to point load, and they are both acting along the side. So that will be equals to minus 65 kilonewton. And this is minus 65. So that means that is a load at the point R. The point half. So that is the same point that is distributing throughout, even at point A. So shear force when x equal to A, that is 10 meter, will be equals to minus 65 as well. Okay, but one thing is that it will be maximum at the point that is it is at the last point. So but something is that is when x is 10 meter, but when x is 5 meter here, that will be 5 times 5, that will be what? 25 plus 15, that will be 40. So when it is maximum, that is when you can have it as minus 15 minus 5 times 10, and that will be minus 65 kilonewton. Okay, like that. Now, for the bending moment, when x equal to A, next thing you find out is that it's always 0, right? Because there's no force, there's no distance action there. 0 kilonewton meter. Now bending moment when x equal to 5 meter. When x equals 5 meter, you know it's acting downward. That is anti-clockwise. Clockwise equals anti-clockwise. This is fixed already. This is acting downward. So while this is acting downward, that will be 15 times. Let's say you want to consider the 5 distance. That will be 15 on its own. Is acting with the distance like you're taking your moment to this side. Okay, so you're taking your moment till half of this. That is what? 5. That'll be 15 times what? Clock, right? You see, it's coming here clockwise. So clockwise equal to anti-clockwise. So it's coming like it's negative. That will be minus 15. Okay, so that will be minus 15 multiplied by your distance 5. Okay, so that will be minus 15 multiplied by 5 minus, okay, this also your UDL, the acting is 5 times that 5. The I is acting as well at this point. Okay, so when I cut this into 2 now, I'm gonna have, you remember the formula for UDL, simply formula for UDL is what? WL square over 2, right? That is WL square over 2, if you remember. That is you cut, when you cut this into half like this point here is also your UDL. Now if I convert this UDL here, which is 5 times 5, that will be 25. Okay, so that is, I'm gonna have 5 times the 5, the distance that is from here to here, the 5 times this 5 distance. Now when you convert UDL, it will come to the center. Okay, so when it comes to the center, you will left with half of this 5 to take it. That will be times 5 over 2. Okay, so that is it, WL square over 2. So what is WL square? That is 5 times 5 square over 2. And remember like that. So you can have it as minus 75 minus, this is 25, 105 divided by 2. That will be 62.5. And here you will be left with an answer like you will left. So 12.5. Now for the next thing, so it's advisable you generate a formula for everything. It's very important. Okay, so also if you remember your UDL, just put the formula, your UDL formula. Remember WS square over 2 for the bending moment, that's for the bending moment. Okay, so also for bending moments when your x equal to 10 meter, you're gonna have it as what? 15. That is minus 15. This is minus 12.5 rather. So that will be minus 15 times total length times 10 minus WL square over 2. That is for even so for bending moment, that will be WL square. That will be 5. L square is what? 10 square over 2. So just put it there. You're gonna have your answer as you're gonna have it is 100 as well. 400. But here is minus 137.5. Okay, that's minus 137.5. That is 75 minus 75 minus 62.5. That is okay, you will have 0.5 kilonewton meter. Okay, so here you're gonna have it as minus 400 kilonewton meter. Now that is that about that. So you're gonna draw a shear force diagram in bending moment. That will be like this. Just come here on your graph, like as explained earlier. Come here on this point, put out your centrality point or your neutrality point. Here, section it equally very fine. So here I put this on here as well. So next thing we'll do is the shear force when x equals to b, that is minus 15. So I gotta put my point minus 15 here. So I'm gonna have something like this. Okay, because of this weight, it will affect here. And next thing is at x equals to 5, that means by section here I'm gonna have something like this. So at this point here, at this point here, that is minus 40. So it will go down a bit. So this is minus 15, minus 40, minus 40. Next thing we have is what? Minus 65. You see, it will go down sequentially. Okay, it will go down sequentially, and you have something like this. Okay, just like your normal UDL, you know your normal UDL diagram is like this. It will to be VDL will be like this. Okay, something like this, and you're gonna have something like this. But this is just a UDL, just a very simple diagram, very straight, and to have an edge here. So this you see is negative. Now bending moment, your bending moments as well, you can just even draw the bending moment often. The bending moment will be something also bend. You remember the bending moment. So let's see. Here you have the bending moment towards 0, and at not at A, rather this is at B, sorry, at B 0, and at x equal to 5 meter you have it as minus 1735. So to be like this, somehow it will be somehow curve, then minus 400, and minus 400 like this. So I'm gonna have something like this. Oh sorry, I'm gonna have something like this. So this is also organ like that, shear force diagram, bending moment diagram thereabout. So that is that about that. Now also let's consider this example as well. Because you need a lot of practical questions on this, a lot that will help you and to help you solve more very well. So this is this very simple sample of a cantilever diagram. It's ENG here, and they put different force. This is 10 kilonewton. This is 20. Here as well is 30 kilonewton, 20 kilonewton, and you have the span, that is the length. You call it span, okay, for you cantilever, and the span here is 1 meter difference, 1 meter difference, 1 meter difference. That makes it 3 meter altogether. That's the question. That's how you're given. That's how you're given. So now you just find the shear force and the bending moment diagram of this question. So what do you do first? You drew what? You drew span. Span is what? 3 meter. You have your point load. There's no point for point load. Everything at point load. So you have your load 1. You just write it there. You just write the particular point you have. So your point load that is W1 is what? 10 kilonewton. W2 point load 2 is what? 20 kilonewton. Point load 3 that is W3 30 kilonewton. Now that is that. Then there's no other this. So you have a point here. You given. If you're not given, just pick a suitable point for yourself. So here is B. Say here is A. Now let's change it as well. Now just same thing goes. No need for RA RB. Just draw the shear force and bending moment diagram. So I want to solve it in this side, and I want to draw the diagram like this. The way they see it, the way they give me the diagram. Yeah. So you got to solve it here as well. So now in this place here, what do you do for shear force? So fast sharp x at point x equal to A. What's the shear force? That is what? Is it negative of what? That is negative of what? 10. Very simple. It's just what? 10. That is minus 10 kilonewton. Shear force. I will draw my bending moment here as well. And put bending moment. So shear force when x equals to 1 meter. You see have it as minus 10 minus 20. Right. That is minus 10 minus 20. That is minus what? 30 kilonewton. You can also plot your table if you want. X equals to 2. Yeah, you can plot your table. Yeah. So x equals to 2 meter. So at x equals to 2 meter, you have it as minus 10, minus 20, and minus what? Minus 30. Okay, so minus 30, that's at x equals, you can see at x equals to 2 meter. So minus 10, minus 20, minus what? 30. You have altogether the answer to be minus what? 60 kilonewton. And now at the last edge, that is at point B, your shear force will still be also equal to the 60 kilonewton. So shear force at x equal to B is just to what? Minus 60 kilo Newton. Okay, because it will just correlate. So since that is 60 kilo Newton, you have it as the first one as minus, that is minus 10. Second one, you have it as what? Minus 10 minus 20, that is when you cut it as minus 30. Okay, so next one is when you get, you have it as what? Minus what? 60. And at this point here, you have it as what? Still continuous as what? Minus 60. So now your bending moment diagram, the bending moment diagram at x equal to b or at x equal to a is what? 0 kilonewton meter. Bending moment at x equal to bending moment at x, bending moment at x equal to 1 meter. You have the reason why I have this as 2 is just 1 plus 1, 2. So bending moment at x equals to 1 meter. That is minus 10. How many distance is it covering? It's covering what? 1, right? So at here, that will be 10 times 1. That is just what? 1 meter. That is just minus what? It's just simply as minus 10 kilonewton meter. Now bending moment when x equals to 2 meter, you have it as 10. You see, it will cover, this will cover at 2 meter. That is if I cut here, that will be what? It will come here. You take your moment right at this point, it will cover, and all force will be directed back to what? To the point. So this one will come here. It will cover a distance of 10, will cover a distance of 2. That will be 10 times 2. That is minus 10 times 2, right? Minus 20 times 1. Minus 20 times 1. That will be minus 20, minus 20, and that gives you minus 40 kilonewton meter. So also bending moment when x equals to 3 meter, I got to map my answer as this. All force will be directed back to what? All forces will be directed back to the edge. I'm gonna have this guy as here. I'm gonna have this one as here. So this is covering 3 distance, total distance, and that'll be 10 times 3. So that'll be minus 10 times 3, and that was minus 30 kilonewton meter. Minus 30 minus 20 times 2, that is minus 40. And also minus 30 times 1, that is minus 30. And I'm going to have my answer as minus 30 minus 70, that is minus 100 kilonewton meter. Okay. So then we're going to draw our shear force in the bending moment diagram. You can plot your table. Okay. So at this point here, let me clean this. Sorry. Alright, yeah. So I can section all these points out on my graph sheet. So I section this as well out like this. So and I section this out so I can have my equivalence diagram very fine. Very good. So shear force here at this point here like this, you can plot your diagram there. So for shear force I have it as what? You can even plot it often. See, let's make an assumption. See, an accurate assumption without a mistake. At this point here, I have this. I know it is what is actually negative, so I keep it here. It drops a bit. It drops towards 10. When it drops to 10, as it comes down, that is minus 10 minus 20. That is minus what? 30. So it comes straight. It drops a bit, minus 30 at this point. When I come here, it comes straight again, straight. When I get here, minus 20 minus 10 minus 20. That is minus 30. Minus 30 minus 30. That is minus what? Minus 60. So it drops to minus 60. It continues. If you see here, you make it correct. Minus 10, minus 20. That is minus 30, minus 60. So here you have your 10, minus 10, minus 20, and minus what? Minus 30 and minus 60. Okay. So this is negative. Now also for the bending moment diagram, what do you have? For the bending moment diagram is very simple as well. What do you do? At this point here like that, so what do you do? From here as well, you have 0 to minus 10. You see, minus 10, minus 40. Like it will decrease accordingly, minus 40. And I will just have it as this. Okay, you have it as straight, and that's straight, no slant, nothing, that's straight, and that is negative. Okay, so that is the bending moment shear force diagram, bending moment shear force diagram for this kind of load for cantilever. Okay.